Hi everyone, let's continue to the subchapter 2-3. It's gonna take a look longer time for this video. It will take only maybe 10 to 15 minutes. I will do very fast as usual. You can read the slide by yourself, go to the column, download the material. Also, you can find any other resources which is uh, applicable or suitable with this subchapter 2-3. So let's go to the slide. So this is the slide for the chapter 2-3, DC voltmeter 2.3. At the end of these topics, you should be able to explain the construction of DC voltmeter, analyze the DC voltmeter circuit. So you can watch this video later. So this is the video about the DR solver movement. I don't want to uh, play the video until the end because you can get this slide and watch later. So if you have this DC voltmeter, if you put this meter here and you put this here, what's going to happen? Okay, what will happen to the meter if 100 milliampere is flowing into it? So it will be destroyed. What do you learn from this problem? Series resistance can avoid the meter from broken, so you have to put a resistance so that you can control the current. The added resistance is determined by the current for full scale deflection and range of the measured voltage. So we need to have this current in order to protect this meter damage. To avoid this, refer the figure below. Right. So this is a simple calculation from the circuit. A voltmeter has full scale deflection of 1 volt. Internal meter resistance is 100 ohm. The meter has 100 microampere full scale deflection. What will be the added resistance value to limit the total current to 100 microampere? So you can calculate the current to ensure that you can limit the total current through the meter. So this is the calculation. So the designer should add 10k to 100 ohm or equals to 9.9 kilo ohm to the 10k minus 100 equals to 9.9 kilo ohm to the circuit. So if you put this value of resistor to the circuit, so you can avoid any damage to the meter. So DC voltmeter, most the voltmeter movement are sensitive devices, have full scale deflection current rating as low as 50 microampere with an internal wire resistance of less than 1000 ohm. This makes for a voltmeter with a full scale rating of only 50 millivolt. In order to build voltmeter with practical scale from such sensitive movement, we need to reduce the voltage down to a level that the movement can handle. The basic DL voltmeter movement can be converted to a DC voltmeter by connecting a multiplier RS with the meter movement. The purpose of the multiplier RS to extend the voltage range of the meter movement, to limit the current through the DR voltmeter movement to a maximum full scale deflection current. So this is the RS, the multiplier of resistance RS, where we can calculate the sensitivity 1 divided by I full scale. So I full scale equals to IN equals to full scale deflection current. This the unit of sensitivity is ohm per volt. So this is the formula where you can get RS plus RM equals to S multiplied by P range. So it is desirable to make R greater than R circuit. R at the voltmeter is greater than resistance in the circuit. Voltage measurement are made by placing the voltmeter across the resistor of interest. So this is how you measure the voltage across the resistance. If you wrongly put the probe then you cannot get the correct reading. Even maybe you can't get the reading. So this is an example. Calculate the sensitivity of a 100 microampere meter movement, used to be which is to be used as a DC voltmeter. The answer is 10,000 ohm per volt. So you can use this formula to calculate the sensitivity. Calculate the value of multiple RS on the 50 volt range of a DC voltmeter that use 200 microampere meter movement with an internal resistance of 1.2 kilo. So the answer is 248.8 kilo ohms. Okay. A multi-range voltmeter. A multi-range voltmeter consists of a deflection instrument, several multiplier resistor, and a rotary switch. So the three multiplier R1, R2, R3 are connected parallel to each other. Only one is connected in series with the meter at any time. The range of this meter is V equals to Im multiplied by Rm plus R, where the multiplier resistance R can be R1 or R2 or R3. So this is the multi-range voltmeter. Okay. The other multi-range voltmeter, the multiplier resistors are connected in series. Okay, it can be also connected in series, and each junction is connected to one of the switch terminals. The range of this voltmeter can be also calculated from the equation V equals to Im multiplied Rm plus R, which is R now can be Ra or Ra plus Rb or Ra plus Rb plus Rc. Okay, the largest voltage range must be associated with the largest sum of the multiplier resistance. So next, multi-range voltmeter. Example 3, calculate the value of the multiplier resistance for the multiple range DC voltmeter circuit shown in figure A and figure B if IFS equals to 50 microampere and Rm equals to 1 kilo ohm. So you can calculate the multiplier resistance for the multiply range DC voltmeter circuit, okay, by using the formula given before. So this is the R1 equals to 59 kilo ohm, R2 199 kilo ohm, R3 599 kilo ohm. So this is for the figure B. You will get the Ra, Rb, and Rc. So next is the loading effect. What is the loading effect in the DC voltmeter? When voltmeter is used to measure the voltage across a circuit component, the voltmeter circuit itself is in parallel with the circuit component. Since the parallel combination of two resistors is less than either resistor alone, the resistance seen by the source is less with the voltmeter connected than without. So this is the loading effect, right? So if you look at this circuit, and then you can see the loading effect. So this is the VRB, RS. This is the current through the meter. So RT equals to RS plus Rm. The total of the resistance total equals to this is in series. Then Req equals to Rb. Okay, this Rb parallel to Rt. Then V range equals to Rs divided by Rs plus Rm divided by sensitivity S. The voltmeter resistance Rt equals to Rs plus Rm equals to S multiplied by V. So this is all the formula which is related to the loading effect. So the calculation Rt equals to S multiplied by V range. Second equation Req equals to Rb serial with the Rt. Without the voltmeter, you will get this value with voltmeter, you will get the value together with the R total, R equivalent, which is RB parallel to the RT. And then you can also calculate the insertion error with this formula. So this is the another example. A voltmeter, a voltmeter 10 to 0 to 10 volt that has an internal resistance of 78 ohm is used to measure the voltage across resistor RB. Determine the percentage of error of the reading due to the voltmeter insertion. Let E equals to 4 volt, RE equals to RB equals to 1 kilo ohm, S equals to 1 kilo ohm per volt. So you can refer back to this equation to solve the example 4. So you can try by yourself. Okay, same goes to the example 5. Okay, you have all the answer there. So in this chapter, we have learned about the purpose of multipliers put in series with a meter movement, calculation of the multiplier resistance of voltmeter, so voltmeter loading effect. So the basic some voltmeter movement can be converted to DC voltmeter by connecting a multiplier RS with the meter movement. Sensitivity S is the reciprocal of the full scale deflection current. Therefore, it is desirable to make the voltmeter resistance much more higher than the circuit resistance. So that's all for the subchapter 2.3. I would like to remind you to download the material from the column, try the example, do the exercise so that it can make you have a better understanding on this subchapter 2.3. That's all. See you again. Bye-bye.